And we're back. All right, today we're going to talk about precipitation reactions, which is another name for double replacement reactions. So we've already talked about double replacement reactions. Remember, they are two compounds reacting with each other. Another name for this reaction is also an ion exchange or an ion interchange reaction as well. In addition to sometimes instead of double replacement, you'll see double displacement reaction, which refers to the fact that the ions exchange or interchange in this reaction. So the reason why this is also called a precipitation reaction is because a solid is forming, and when a solid forms in a reaction, that is called a precipitate. So that's the driving force behind these double replacement reactions, is due to the fact that a solid forms. If you have a reaction like this, a double replacement reaction, two compounds interacting, and no solid forms, then no reaction will occur. So no reaction will occur when, so you have two different ionic compounds, if they're dissolved in water, the resulting solution contains the separated ions, so if no solid forms, then those ions will just be left lying there in solution. Okay, so an example of a precipitation reaction is the reaction that is going to be shown here. So we have a beaker on the left, which contains barium nitrate. And always you'll be given your ion chart, so you'll know the charge of nitrate. So in here, barium nitrate is an ionic compound. It's an ionic solid, but when it's dissolved in water, it becomes aqueous. And when it's dissolved in water, it breaks apart into its two different ions. So we have, in this solution, barium ions, as well as two nitrate ions, since it's BaNO3 2. Okay, so those are the two ions we have on the beaker on the left. The beaker on the right is potassium chromate, which is K2Cr4. So that means in here we've dissolved that solid potassium chromate in water. So the two ions in that solution, we have two potassium ions, since it's K2, as well as one chromate ion. Okay, so that's all of the ions that are present separately. So now what we're going to do for this reaction, we are going to mix them, and we have to figure out, okay, what solid is going to form. Because we now know this mixed solution contains the following ions. So it contains potassium ions, chromate ions, barium ions, and nitrate ions. And we have to figure out, okay, what combination of those forms this yellow, white, milky solid that's produced in this reaction. Okay, so a couple of rules that have to be followed. So we know automatically our final compound must have zero net charge. That means the product must contain both cations and anions. So that means if we had both, like let's say potassium ion and barium ion and a barium ion, this would be impossible. These cannot form a compound. They're both cations. Since they're both positive charges, it's impossible for them to combine and form a neutral compound. And the same is true for the nitrate anion and the chromate anion. These can never combine to form a compound since they're both negatively charged. They can never form a neutral compound. And one other rule is that normally there's only one cation and one anion in an individual compound. And so if we look at all the compounds from our previous slide, so the K could go with the chromate ion, CrO4, or with the NO3. So it could be K2CrO4 or KNO3. So those are the possible compounds that could be formed, except we already know one of the starting materials, one of the reactants, is potassium chromate, this K2CrO4. So we automatically know that that cannot be a possible product. And it's the same thing for thinking about the barium ion. It could either react with the chromate or with the nitrate ion. So the two possibilities there are BaCrO4 or BaNO32. And already we know BaNO32, barium nitrate, that was one of our reactants, so that's not going to reform. So that means these potassium nitrate and barium chromate are going to be our two products. And this is a good visual for us. This, at letter A, is before all of those start reacting, and then B is when they are actually reacting. But now we have to figure out, okay, what part here, if you look at the bottom, forms this yellow-white precipitate, and which ions up here do not participate in the reaction. So we actually know that the substance that forms the precipitate is barium chromate, the substance that forms the solid. And we only know this from the rules for solubility. So some substances, some compounds are what we call soluble, and some are insoluble, which form these solid products, these precipitates, in double replacement reactions. Okay, so we know in this case, barium chromate was insoluble. It did not dissolve in solution. And anytime something doesn't dissolve in solution, it is a solid, so using S in the reaction. While the other compound, so in this case up here, this was potassium nitrate, that was soluble. Those ions are still in solution. Up here you have potassium ions and nitrate ions that are soluble, meaning they dissolve in solution. So they're still ions when dissolved in water, meaning they are aqueous. So AQ represents that. And normally we'll just use these two terms, insoluble, which indicates the solid product, the precipitate, and soluble, meaning those ions are still present in solution, and it's aqueous. And sometimes you'll see the term slightly soluble. If you ever see that, just assume it means insoluble, because that slightly soluble means that, yes, it can dissolve, but only very, very slightly, like below 1%. So you can just assume that that is insoluble. Okay, so following this, there are rules for solubility, and these rules will always be given to you along with the ion chart. So we can use these to correctly identify that for the previous reaction, which one was the solid precipitate. So we know we started with our two starting materials, our two reactants. So we had barium nitrate, and always your two reactants will be soluble in solution. They'll be aqueous. And you can assume this, and you can also check with the solubility rules. So BaNO32, barium nitrate, most nitrate salts are soluble, meaning this is aqueous. And it reacted with potassium chromate, K2CrO4. And if you look at rule number 2, most alkali metals, group 1, potassium's in group 1, so they are soluble, meaning that that is aqueous. Okay, so now those combine to produce the following two products: barium chromate, where if you look at rule number 6, it says most of these following anions are only slightly soluble. And remember, we assume that means insoluble, so that's the solid product. And then the other product here, potassium nitrate, if we refer back to rule number 1, most nitrate salts are soluble, so that is aqueous. So that's how we're able to predict which one of these will produce a solid product. Okay, and this formula that was just written is called a formula equation or molecular equation. And that's exclusively what we've seen up to this point, where you use those mole ratios, you look at the reaction stoichiometry. But what we just saw, that wasn't the actual form of the reactants and products in solution. So yes, there is compounds, but in an aqueous solution, they actually exist as ions. Okay, so another example here. So let's say we have the reaction of silver nitrate, AgNO3, and that is aqueous if you refer to rule number 1. Most nitrate salts are soluble, and it reacts with table salt, NaCl, and that is aqueous if you refer to rule number 2. Most of those alkali metals are soluble. And now we have to predict the two products. So we know this is double replacement or double displacement, and we know all of these exist as ions in solution, so the Ag replaces or displaces the Ag plus ion, displaces the Na plus ion to react with the Cl minus ion to produce AgCl. And if you look at rule number 3, yes, most Cl minus salts are soluble, except there are 3 exceptions, one of which is Ag, making it insoluble. So that means that's our solid product, meaning a reaction will occur. And then the reverse is true. The Na replaces the Ag. So it's Na, and it's reacting with the nitrate, the NO3 minus ion. And if you refer back to rule number 1, that makes this aqueous. And always with these double replacement reactions, there's never 2 insoluble products. There's never 2 solids. There's only one compound that is the solid product. So this is the formula or molecular equation for this reaction. However, that's not how these actually exist in solution. For all of these aqueous compounds, they actually exist as ions. So in order to represent that, we use what's called the complete ionic equation that represents all reactants and products that are strong electrolytes or that are soluble or aqueous. It represents them as ions. So using that previous example, AgNO3 was aqueous, so we break that apart in solution into the silver, the Ag plus ion, and if it starts as aqueous, it remains aqueous. So we break AgNO3 into Ag plus and NO3 minus. And then the next one, the next reactant, NaCl, is aqueous, so we break that apart into its 2 ions, the sodium Na plus ion and the chloride ion. So those are all of our reactants. Now, if we look at our products, AgCl was a product, except it was a solid. So if something's a solid, it still exists as a solid in solution. It does not break apart. So we still write any solid the exact same way. It remains intact. So AgCl is a solid. Then we look at our final product, NaNO3, which was aqueous. So therefore it breaks apart into its two ions, the Na plus ion and its nitrate ion, NO3. So this is the complete ionic equation. Now next we have the net ionic equation, which includes only those in the solution that are undergoing a change, or only the components that actually react to form the solid product. So what it does, it eliminates what are called spectator ions, so those that don't participate directly, or those that are present in both the reactants and the products. So if you look at this example, the following ions that are present to the left of the arrow as reactants and to the right are both Na+, present on the left and on the right, as well as NO3. The nitrate ion is present as both a reactant and as a product. So those two, Na+ and NO3, those are called spectator ions since they don't participate directly in the reaction. They're present on both sides of the equation. They're present before and after the reaction. So now for writing the net ionic equation, we literally just rewrite everything we have not crossed out. So the only species that are left here is the reactants, Ag+, the silver ion, and the chloride ion. And the only product that's left is AgCl as a solid. So one thing I want to point out for the net ionic equation, the solid product will always be the only product, and the two reactants should both be balanced in terms of number of atoms with the product side, and the charge should be balanced. These should add up for an overall charge of 0. So these are always the two ions that make up the precipitate. Okay, so this one was a relatively easy reaction to deal with since there were no coefficients and there weren't any subscripts as well. So the hardest part of this is when you're given a word equation and need to transfer it to a formula equation. And you should be able to write not only the formula equation, once you write that, the complete ionic equation, and also net ionic equation. So if you look, we have the reaction cobalt-2 chloride. So that cobalt-2 means it's CO2 plus reacting with chloride, Cl minus. That means that is CoCl2. And looking at your rules, so if you look back at your rules, rule number 3, most chloride ions are soluble, so that's aqueous, and it's reacting with sodium hydroxide, so Na plus and OH minus, so that's NaOH. And if you look at rule number 2, most of those group 1 ionic compounds are soluble. So like I said, both of the reactants will always be aqueous, and if you end up getting your reaction where it produces two products that are aqueous, then no reaction will occur since all of those ions are just staying in solution. Okay, so now we can predict the two products. So now the cobalt ion, the CO2 plus ion, will replace the Na plus ion to react with the hydroxide, so COOH2. And now, if you look back at rule number 5, most OH- are only slightly soluble. Only some are soluble, and that does not include the COOH2, so that means this is insoluble. So it's a solid product, and then the Na plus replaces the CO. So the Na plus is reacting with the chloride, the Cl minus ion, so NaCl, and we know that is aqueous, that dissolves in water. However, we are not finished yet. We need to make sure that this equation is balanced. So if we look here, the COs are balanced, except there's 2 chlorides on the left side, so we need to make sure there's 2 on the right. So we put a 2 in front of there, NaCl, and now there's 2 NAs on the right, so we need to add a 2 here. So now on the left side there's 2 OHs. On the left side there's 2 OHs, and now already there's 2 OHs on the right side, so now our equation is balanced. Okay, so now for writing the complete ionic equation, it's a little tricky here. So now COCl2 is aqueous, so it breaks apart in solution, so it breaks apart into CO2+, and it doesn't break apart into CO2+ and Cl2 with a -1 charge. That Cl2 means there's 2 chloride ions. So when writing the complete ionic equation, that 2 now becomes a coefficient to indicate that there are 2 chloride ions. And then the tricky part for the next one, 2 NaOH, that means there's 2 NaOH ionic compounds there. So that applies to both the sodium, both the Na and the OH ions. So that means there's 2 Na plus ions there, as well as 2 OH minus ions. So just be careful you don't just apply it to just the first compound, just the Na. You have to apply it to the entire compound. And now if we look at our products, the first product remains exactly the same since it's solid, since it will not break apart in solution. So that remains exactly the same. And then finally, 2 NaCl, that breaks apart into 2 sodium ions. It's still aqueous, as well as 2 chloride ions, which are still aqueous as well. So now before writing the net ionic equation, we have to identify our spectator ions, those that are present before and after. And these numbers of the spectator ion should always match. So for example, here on the side left we have 2 Na plus ions, and on the right side there's 2 Na plus ions as well. So those spectators, those numbers should always match. And if you look right next to there, we have 2 Cl minus ions as our product, as well as a reactant. So now for the net ionic equation, we're just writing the ions that participate in the reaction, or those that are left over here. So we have the cobalt ion reacting with the hydroxide ion to produce the solid product, the precipitate, COOH2. And if you look, these number of ions match up, and the charges balance out. There's any solid product, any neutral compound has a charge of 0. And then on the reactant side, there's a charge of +2, and 2 minus 1 charges, meaning the charge is neutral. And also for these net ionic equations, just like balancing any equation, it should always be in the lowest whole number ratio. Okay, so you should be able to first write the formula equation, be able to identify whether a product will be aqueous or solid, which one's the precipitate. Then from that, be able to break everything that is soluble, everything that is aqueous, into its ions, into the complete ionic equation. And then from that, identify the spectator ions and write the net ionic equation. All right, that's all for today. See you next time.